Let's get started. So the new topic for the week is control. With sample-based methods. What is control? Let's have a dialogue. To control something. What does it mean to control something? I see. To make decisions. So what do we mean by control in our context, in the context of reinforcement learning? Previously, we were talking about prediction methods. That were about learning value functions. So in control, what do we want to learn? I think someone wants to get in. Okay. So what do we want to learn in control? Right. Our goal is to learn the optimal policy. If we have the MDP in our hand, we're in an MDP. There are these policies. And we just wanted to get an optimal policy. How would you get an optimal policy? How would you compute an optimal policy? Give me the names of some methods that would do that for you. Yeah. Policy evaluation, policy iteration. Yeah. Policy iteration would be a good way So recall what policy iteration does. Picks a policy, evaluates it. Maybe it gets the action values for the policy, and then computes the greedy policy with respect to the action value function that we got, and repeats this process until convergence. That was policy iteration. Give me some other method. What would be another method? Huh? Yeah? What? Monte Carlo? You have the MDP. Why do you need Monte Carlo? Sure. Oh, Monte Carlo is searching for an optimal policy? Oh, so. What does it do, Monte Carlo? Following a policy? Or how is the trajectory generated? Well, the trajectory may or may not be random if the MDP has random transitions. Well, how do we select the actions for the trajectory, right? Like, actions are part of the trajectory. Following a policy. Follow a policy and then do these rollouts. And then Monte Carlo can be used to estimate the values of the policy. Does it give us a better policy? Oh, maybe you're thinking about some other Monte Carlo method.
Some trajectories are better than others. Find what policy the better trajectory.
Okay. I guess you're developing a new algorithm that we didn't learn about in your mind. That's okay.
Some trajectories are better than others.
Yeah. So you have a starting state, and then you are rolling out. Maybe if you arrive at a state, then you choose some random action, go somewhere. So you have a bunch of trajectories. Let's say these are in state action space, and you see the associated returns. What do you do then?
Find which trajectory gives the most reward, and remember the policy in the action choice in each state,
Right.
and that should give you the policy.
That's very interesting idea. I don't think that it was in the book or anywhere, but
Oh,
is it? Am I missing something? I think we can credit this algorithm to you. No, okay. So truth to be told, other people also thought about similar things. Yeah, but okay. So that's interesting. So you have the states, and then you can remember what action you took, and like. But okay, so let's say this trajectory has a reward of 100, and all these others lead to a reward of 0. What can I learn from this? I guess more realistically, you would see a bunch of tens and like a distribution of returns along the trajectories. I think it's a longer conversation to figure out how to get a better policy from this. But
it's from this random sampling, you should be able to eventually find the optimal policy. Eventually.
I think, yeah, like I agree with the statement that if you're collecting a lot of samples, then eventually the information is there. The question is, how do you get an algorithm that processes that information? So I can imagine here things like, I don't know, like trying to use some sort of supervised learning for, I don't know, just selecting the top 10 percentile of the trajectories, and then use that as a supervised learning data set where you have states and then associated actions, and you try to learn this relationship. And then you're hoping that that will give you a good policy. So people are thinking about things like that. This is not what we talked about before. And it has some problems. So many times, the problem is that what we want to maximize is expected return and not the random return. So just because a trajectory led to a good return doesn't mean that if you're taking actions associated with this trajectory, you will again see a large return. It could be just chance. That's
the same trajectory multiple times.
right. Well, and you hope that eventually things are, somehow you can wash out the noise, but that's where usually these incremental update algorithms come in that try to compute expected values before optimizing. So there's always a question of like, when do you optimize? Like, do you optimize first and then compute the expected values, or first kind of approximately compute the expected values and then optimize? And the methods we're talking about typically do the second, and for a good reason, because the values themselves are defined in terms of expected values. So first, you average a lot somehow with Monte Carlo or whatnot, and then you apply some optimization because you want to wash out the noise. You don't want to jump on false signals of like, this is very promising, but maybe it's just due to chance. Anyways, interesting. So going back to my original question, you have the MDP, it's finite. You don't have to sample. What is another method that allows you to calculate a near optimal policy quickly. What? What? Something else? Some new idea?
I'll think of something new.
Okay, fine. Tell us.
I don't know.
Okay. What is it?
I don't have any.
Okay, so we did learn about some really specific methods that go by some very specific name. Iteration is part of the name, but it doesn't start with policy. What is that? Yeah, value iteration. Okay, remember these. Value iteration, policy iteration. Those are two foundational ideas to get near optimal policies quickly in small MDPs. All right. So these methods, on the other hand, are not doing any learning. They assume that they are given a description of the MDP, and they apply, these algebraic operations repeatedly, and eventually they come up with a policy. When we're talking about learning, we're thinking about that, oh, the MDP is not given to you, but you have some way of accessing the MDP. How do we access the MDP? There are multiple ways of thinking about this. So maybe you're interacting with a real system, and the real system is modeled the MDP. This is the MDP. In interacting with the real system, we have this little graph that we had at the beginning of the class, where you have the controller sending actions to the system, which could be the MDP, which sends back observations, in this case, rewards and next states to the controller. So this is what I call online access. So here, the only way to access the MDP is that the MDP has its internal state. The only way to manipulate the internal state of the MDP is to send an action. So the interface to the control system, the MDP, is very narrow. You can just say, hey, here's an action. Give me a reward and a next state, given your current state. And whoever is processing this information has to keep track of what was the previous state. Then they can do whatever they want to do with this data. So there is this interaction that can go on for a while. So notice that here, we didn't really have the transition properties given to us or the immediate reward function given to us. We are just having a sample access, but it's a very specific sample access. You can just follow a single trajectory in the MDP. There is nothing else that you can do in this case. So sometimes people, so this is appropriate if you're controlling a real system. If you're controlling a real system, most of the time, this is the only thing you can do. Sometimes what you can also do is that you can have resets. You can have online access plus reset. And the reset, that just means that setting the state to a particular state. It could be an initial state that you're interested in. It could be a state sampled from some distribution. But it's kind of like breaking up the trajectory. So it's like you're not following the trajectory for a while, and then your controller decides it's time to reset. In the context of interacting with a real system, resets may or may not be there. So for example, if you have a robot arm, and we want the robot arm to accomplish some tasks like pick and place, then someone like a reset would correspond to executing maybe some sequence of actions such that the robot arm goes back to some default position. Let's say it's like lifts up and like in this weird position. And then that's the state that we are resetting to. Then someone needs to give a controller that from no matter like what state the robot arm was before, makes it so that the new, like after the reset, after executing this control policy, the new state is this specific designated state. So that's online access plus resets. Sometimes you have a simulator. And if you have a simulator, then the reset could be very simple. It's like the simulator has an internal representation for the states, just reset that state to some particle value. If you have such a simulator, then you can maybe reset to any particular state. And so if that is the case, you know the whole state space, and you can reset to any particular state, then that's called global access. It's global because the whole state space is given to you. When you have this very thin initial interface, it's very rare that you would know all the possible states that can viably be reached at all with any strategy. So for example, taking the robot arm example, if you have a robot arm and it has to operate in some cluttered environment, maybe this is the arm and it needs to go, and there are some objects, and it shouldn't bump into objects like this water bottle. So there are illegal states then. So the state that would like push over this water bottle, this state, would not be a legal state. And it may be very complicated to know in advance which states are going to be legal and which states are going to be illegal, admissible or unadmissible. And therefore, it may be very, very hard to know ahead of time that to have a simulator that has global access, real global access in a complicated scenario, because you can write the dynamics for the robot arm and everything, but just calculating which states are free and which states are not free of collisions is a hard calculation, and it's just computationally too expensive for people to do. So this global access is not too realistic. When people talk about global access, they also call this the generative model assumption. So sometimes these algorithms are studied under these different access models, and they will have different properties. So under this access, global access, you can do anything that you can do under online access plus reset. And under online access plus reset, you can do anything that you can do under online access. So it's more powerful to be in the bottom of this list than on the top of the list if you are designing algorithms. It is a more advantageous situation to be here than there, because your algorithm can use a richer interface, so it can do more things, and maybe it can save you computation if you have richer access. If you're interacting with a real-world system, then you most likely only have this, and if you wanted to have something like this, then you would need to work really hard to get these resets done for your system, if it can ever be done. OK. So the difference between the setting that we talked beforehand for control and the new setting is that in the new setting, you have this scene interface to the system. You don't have all the transition probabilities. And with the scene interface, you still want to be able to get a near optimal policy. The question is, how do we do this? What are the challenges that we are facing? And you've already read about this, and you read a few algorithms. And what I would like to point you to at this moment is only that almost all the algorithms out there in the literature which are successful, okay, so there are two big categories. There is going to be the direct and the indirect methods. Some people call the direct methods pure value-based methods. And the indirect methods, they're calling them model-based methods. So what I wanted to say is that if you look at the algorithms that people are implementing, no matter actually whether you are in the direct or indirect category, eventually you're going to use some variation of these two basic algorithms. It's kind of really interesting that everything kind of goes back to these, and you will be very, very hard pressed to see anything else. So people who are familiar with the literature might object and say that, oh, policy gradient. So what's policy gradient? I think it's also in a book somewhere. Maybe you haven't read about it. Following gradients, you have heard about it, right? So following gradients, you have an objective function and you want to, let's say, minimize it, or you want to maximize it, and you just follow the gradients of the function in the weight space or whatever, right? And so you can imagine that you have a policy parameterized with a neural network, and somehow the performance as a function of the parameters, it's a function. You want to optimize it. You follow the gradient. That's policy gradient. And you can write some equations. You can get a sample-based method for doing this policy gradient things. And they don't seem to fit this picture of doing policy iteration or value iteration. At the end of the day, if you are pressing it really hard, the methods that people are using still going to use some value estimation component, because it happens that it's just the gradients are way too noisy most of the time, unless you're using some value-based method. So I think that it's maybe a little exaggeration to say that everything that is successful today is derived from these two things, because, okay, there's this policy gradient idea, and it's kind of a muddy thing. But at the end, those algorithms also use some component of value estimation. And if you're squinting hard, then you might be seeing policy iteration in those methods as well, because it's updating a policy. And in the meanwhile, it's estimating the value function of a policy. So it's like okay, where does it stop being policy iteration? Where does policy iteration start, and where does it end? There is a continuum of these things. But I think that it's good to keep in mind that, okay, like this view that, okay, like there are these basic two different things that you can do, policy iteration and value iteration. And if you see an algorithm, try to see which one of these is closest to the method that you're saying. Anyways, so the point is that we can have a learning version of policy iteration and value iteration, both of them, and actually many variations of them. So how does the algorithm look like? Okay, let's start with value iteration. So value iteration, yeah. Oh, what is the difference? You don't have the MDP. Isn't the big difference? Huh? If you have global access, you still don't have the MDP. I mean, like, you can build an MDP. You can build a model. Okay, so maybe going back to here, there is this distinction between these two types of methods, the direct methods and the indirect methods. In the indirect methods, you take your samples, you build a model, and you try to apply some technique that works against optimizing for a model, right? Now you have a model, now you can try to compute an optimal policy for the model. So if you have global access, the simplest thing would be, for every state, for every action, get a bunch of transitions, use sample averages to calculate transition probabilities to the next states, calculate an estimate of the immediate reward function as well for every state action pair, and then run any of the two algorithms, policy iteration and value iteration. So under global access, this is the simplest thing you can do. And it turns out this is kind of the best you can do. You will not be able to do anything much more clever than this under global access to a first degree approximation. So in terms of, OK, so when we're talking about methods that are trying to find a good policy, we should also think about how are we going to compare different methods. So Shivam is going to suggest one method, maybe Shwai suggests another method, another method, and so forth. Who is winning? Well, it doesn't have to be winner, but in this case, one metric that people use to evaluate this is how many samples did we need to get a near optimal policy. So you fix an epsilon, that's your target, accuracy. I want an epsilon optimal policy. And you ask yourself, how many samples do I need to sample from this MDP in order to get this epsilon optimal policy? And it turns out that for this very simple method that I described, we just use this global access and uniformly for all state action pairs, just like samples, same number of next states and rewards, does this averaging, then solves the resulting MDP. The sample complexity for this guy is, sample complexity is like how many samples does it need in order to get an optimal policy with high probability. It's number of states times number of actions, because for every state action pair, it has to do a little work. And for each of them, it has to sample h cubed over epsilon samples, where h is this effective horizon if you're in the discounted setting. Sorry, epsilon squared. That's how many samples it needs. Maybe there's some constant factor that I'm just ignoring there for simplicity. So we can see that this scales linearly with the number of states and actions. It scales cubically with the horizon, inversely quadratically with the precision. So epsilon was the target accuracy. So we wanted to have a policy pi such that the value function of this policy is not further than epsilon away from v star, the optimal value function. And this number of samples, you can prove that in a worst case, it's necessary. No method can do better than this in a worst case sense. So in a sense, like worst case, this is optimal. Then you can go and think about whether there is a finer distinction between algorithms. OK, so maybe there are multiple worst case optimal algorithms. Which one do you want to choose? That's too complicated. We're not going to talk about that. But there are ways of choosing in between algorithms, even if all of them are worst case optimal. We talked a little bit about this at the very beginning when we were talking about just sorting algorithms, right? You remember that discussion at the very beginning? I was like, oh, would you use bubble sort? No, I wouldn't use. But maybe I would use bubble sort if things are almost sorted. And so it depends on the distribution of things and so forth. So you can have something like that here as well. But in terms of worst case optimality, this is the best you can get. And this very simple method gets it. Doesn't matter how you solve the MDP. You can solve the empirical MDP either with value iteration or policy iteration. That's fine. Okay. Your question, Shimon, was how is this different from knowing the MDP? Well, we see that sometimes we just reduce things to knowing the MDP. The difference was that, well, we had to somehow collect the samples to estimate the MDP. And so on the global axis, this was very simple because I can just reset to any state action pair. I can get next states and rewards from there as many as I want. And it's cheap. Under online access or online access with a reset, this may or may not be cheap. Because you can imagine easily an MDP where, like there is a garden path to somewhere, and it's really hard to get to that part of the state space. And so if you want to have a performance that is good everywhere, then you have to figure out kind of like how to navigate in the MDP, which may be as hard as, like everything that we want to do. So it also feels like there is a chicken egg problem there. You will need to be able to navigate the MDP before you know the MDP. Like, how are you going to do that? So the name for this problem that comes when you have online exploration and maybe or online access. When you have online access and maybe online access on the reset is the exploration problem, right? So exploration is not a problem under global access. Exploration may be a problem under online access. All right, let's put that aside. But I guess we understand now that if you had the MDP, then you definitely do not have any exploration issues. You only have computational issues. You don't have the MDP and you only have online access, you definitely have an exploration issue that you need to address in some way. That's a fundamental difference. All right, going back to my pitch, value iteration. So let's pick value iteration. We want to build a method around value iteration that uses maybe online access. So you have the thinnest interface. What is the method that you have learned about if you read the book for this week? What are the cursor exercises that kind of mimics value iteration and tries to do this job? You remember this? It's too early in the week, maybe. Huh? Any hints? Yeah, it's like, what does value iteration? Well, I guess the question is hard in the sense that, like, if you didn't actually read the thing, then we can derive the thing, but you won't know the name of it. But OK, so there is a hint. So value iteration. You can do value iteration with state value functions, and you can do value iteration with, what is the other thing? Action value functions. That's right. Value iteration can be done with state value functions, and it can be done with action value functions. What's the cool thing about doing things with action value functions? And what's the uncool thing about doing value iteration with state value functions? What does value iteration do? Calculates a sequence of functions that assign either to states values or to state actions values. Fine. What do we do with these functions? We're trying to solve a control problem. We need to get a what? Policy. That's right. In a control problem, we want to get a policy. How do we get a policy given such a function? What's the plan? That's right. So if you have an action value function, how does it look like? Usually we use a letter Q, but you could use any other letter. It's a map from state action pairs to reduce. And if you have such an action value function, then you can take a policy which chooses a state as an action that maximizes this function of your choice, Q. So value iteration computes for you a sequence of these if you apply it with action value functions. And then the plan is just to greedify with respect to this action value function that we calculated. Take a greedy policy. So that's cool because it's simple. You can get, if we had this theorem that, okay, maybe we didn't show it for the Q functions, but we showed something like that. If a Q function that you calculated, an action value function, is close to the optimal action value function, the policy that you're reading out is guaranteed to be also near optimal. So as this Q approaches Q star, this policy pi approaches pi star. And that's why this is a good plan. There is this stability. It's like Q star, you deviate from it a little bit. OK, from pi star, you also deviate a little bit, maybe a little bit more, but not too much. OK? So that's cool. If you have state value functions, what can you do? What's the plan there? You want to say so? Sure. Right. You do have to use the model to do a little look ahead, right? So compute the reward under the action plus gamma times like wherever that action is going to go and evaluate the future states with the value functions. That's like a one-step look ahead calculation with the model. Do we have a model? If we are in the learning case, online access? No, unless you build one, right? So that's not cool. If you were not planning on building a model, no, you're kind of forced to build a model, even if you just want to use this state value function kind of iteration thing and do the greedification. So that's complicated. Yes. That's right. You can. It just, like it's too many moving components. It's not as cool as not even building a model. It's a valid thing to do, and it won't be bad. It's just slightly more complicated than not doing it, but just learning action value functions. But it's worth it. All right. So the conclusion here is that maybe we prefer value iteration with action value functions because it is like without having access to a model, we can, if the action value function becomes precise, we're granted that we will have a simple way of knowing how to act in a near optimal fashion. And that's a simple plan. So we are iterating on these Q functions. OK. But that's like uses the model, right? It's value iteration. It's like apply the Bellman optimality operator that uses the model. What if you don't have the model? Can we do the same? And how is the algorithm called? What are we learning? What functions are we learning? Q functions? So how is this algorithm called? Oh, yeah, it's called Q learning. All right. Oh, and people, okay, historical reasons, all these letters are uppercase, whatnot, so you write it with uppercase, Q learning. Okay. So Q learning, you can think about Q learning as taking value iteration and making it a sample-based method. Also, we have seen the same thing being done with TD learning for learning value functions the last week. It's the exact same idea, right? So for TD learning, we had, this is a little bit far. So with TD learning, what we had is that we had this abstract version of it, TD learning. We had a policy that was fixed, and we developed like 3 different versions of TD learning. We were saying, okay, you can have this parallel TD learning kind of thing where you're updating all states, and you use the model here. So that's kind of mimics value iteration applied with the T-pi operator, this policy evaluation operator, but it kind of softened up with this convex combination. And the reason we do these convex combinations is because we want to have noise. And we want to be able to, we don't want to have noise. We have noise, and we have to deal with the noise. And so this T-pi V at S, remember, this is RSA plus gamma times so this is sum of reactions, probability of the action, and then reward plus gamma times sum over next states, the values of those states. So this was the operator that we had. And so now we have this reward plus gamma times next thing. So a sample-based version of that is just to write the reward plus gamma times a sample from this distribution. So this RT plus 1 is a sample from here. And this V of T at ST plus 1 is just a sample of this. Okay, so that was TD learning. So if we want to write the similar update rules for value iteration with action value functions, we can. So we can write the analog to the first equation. It's just going to be Q of T plus 1 is equal to 1 minus alpha T times QT plus alpha T times T applied to QT. Where, okay, what is T applied to some function Q? Well, it returns an action value function, and it is what's written here, except that you have to take a max inside. So, T tilde. Oh, yeah. Sometimes I abuse the notation and I just use T everywhere for Bellman optimality operators, regardless of whether they're acting on value functions, state value functions, or action value functions. But OK, if we don't abuse notation, we had this notation before. T tilde was the notation that we were using in the context of action value functions. And OK, lots of writing. All right, so this is the corresponding operator. And now if we want to have a sample-based version of this, it's very simple. I just have to look at what happens here on the current sample, and then have a sample-based version of this expression. And what is that? So qt plus 1 st80 is going to be 1 minus alpha t qt st80 plus alpha t. And then now, OK, I have to look here. We need the reward. So that's our t plus 1. And then we need this expected value. We don't want to write the expected value, sums, and whatnot. We just take the next state. So forget about the sum. S prime becomes equals to st plus 1, and just write the resulting expression. And if you recall the argument I was making before, is that the conditional expectation of this expression given the current state and Vt is equal to this. Similarly, the conditional expectation of this given the current state and action, well, small q, big Q, and Qt is going to be equal to this. That still holds. It's a complete analog of TD learning, except that now we apply it with the Bellman optimality operator developed for action value functions. That's Q learning. All right, cool. So we have our first sample-based method. And now you can imagine how you do this for policy iteration. You can have many variations of that. I'm not going to talk about it. A lot of times people just call this actor critique methods. So the sample-based versions of policy iteration are these actor critique methods. It's a weird terminology. It's another kind of literature. The critic is estimating values, and the actor is just a policy or a controller. And you are simultaneously updating this and that. All right. So what is missing here? We are doing this under online access. What is the big part that is missing? Is this going to work? Let me just do this. OK, I didn't say how we're choosing the actions. We have to be clever about how we are choosing the actions. If we are just choosing the actions in a greedy way, to go back to bandits, that would be like a greedy algorithm. And it's going to fall trap of jumping on shadows, right? It's not going to be clever if initially something looks great. It's going to stick to it and will not try other things. It's not exploring. So in order to have a good algorithm built around Q-learning, one also needs to figure out how to explore. So next time, we're going to talk about these different ways of exploring under online access and how you should be doing that, and whether we have any good solutions for that. All right, good discussion today. Thank you.